What if everything you see around you, the stars, the galaxies, even the air you breathe, is just the surface of something far deeper? Picture standing at the edge of an endless ocean, knowing that beneath the waves lies a world unseen, teeming with mysteries beyond comprehension. That's exactly how some of the greatest minds in history have described our universe, not as a single, flat reality, but as a multi-layered masterpiece, hiding dimensions and realms we can't even begin to perceive. For centuries, philosophers, scientists, and dreamers have dared to ask, what if we're not alone in this cosmic expanse? What if there's more to existence than meets the eye? From the ancient teachings of Eastern mystics to the equations of modern physicists, the idea of a multi-layered universe has fascinated and haunted us. Think about it. What if the darkness between stars isn't empty at all, but a veil separating us from other realities? What if black holes aren't just cosmic vacuum cleaners, but doorways to hidden dimensions? These aren't just wild speculations, they're serious theories explored by some of the brightest thinkers of our time. And today, we're going to dive deep into these mind-bending ideas, unraveling the clues that suggest our universe is far stranger and more interconnected than we ever imagined. This journey won't just challenge what you know, it might rewrite how you see reality itself. We'll explore how ancient cultures hinted at these hidden realms long before telescopes or quantum physics existed. We'll unpack the cutting-edge science that suggests parallel universes could be brushing against our own, like shadows dancing just out of sight. And we'll confront the haunting question, if there are other layers to existence, what or who might be lurking within them? By the end of this exploration, the night sky will never look the same to you again. So take a deep breath, open your mind, and let's step into the unknown together. The universe is waiting, and it has secrets to share. To grasp the enormity of a multi-layered universe, let's peel back the first layer together. Imagine reality not as a single sheet of paper, but as an entire book, each page a separate dimension, vibrating just beyond our senses. This isn't science fiction. Ancient Hindu texts described reality as a cosmic lotus, with each petal holding a different world. The Greeks spoke of the Platonic realms, perfect layers of existence beyond our flawed perception. Even indigenous cultures shared myths of spirit worlds overlapping our own, accessible only in dreams or sacred rituals. Fast forward to today, and science is catching up to these ancient whispers. String theory, one of the most ambitious frameworks in physics, suggests our universe might have 10 or even 11 dimensions, most curled up so tightly we'll never see them. Think of a garden hose stretched across a field. From far away, it looks one-dimensional, but up close, you realize it's a tube with hidden depth. Our universe could be like that, with extra dimensions folded into the fabric of space-time. Then there's the quantum realm, where particles flicker in and out of existence, as if dancing between layers. Experiments show electrons vanishing from one place and reappearing in another, defying classical physics. Could they be slipping into adjacent dimensions? Some theories even propose that dark matter, the invisible glue holding galaxies together, might be ordinary matter leaking into our universe from another layer. But here's the real mystery. If these layers exist, how do they interact? Some scientists speculate that gravitational anomalies, places where gravity behaves oddly, could be wrinkles where dimensions touch. Others believe cosmic rays with unexplainable energy might be echoes from parallel realities. The more we explore, the more the universe feels like a grand symphony with notes we're only beginning to hear. So what does this mean for us? If the cosmos is truly multilayered, then every empty space might be teeming with unseen activity. The night sky isn't just stars, it's a curtain, and behind it, countless other stages where entirely different stories unfold. This isn't just about hidden dimensions, it's about redefining what's possible. If ancient wisdom and modern science both point to the same staggering idea, maybe we're standing on the threshold of the greatest discovery in history, one that could reveal we've never been alone in the cosmos at all. String theory isn't just a fringe idea, it's one of the most promising frameworks we have for understanding the hidden architecture of reality. Picture the universe not as a collection of solid particles, but as a cosmic orchestra where every tiny string vibrates at its own unique frequency. These vibrations aren't random, they're the very essence of matter and energy, the notes that compose everything from stars to stardust. But here's the twist: for the math to work, these strings can't just dance in the 3 dimensions we know. They need at least 10, maybe even 11 dimensions to move through. So where are these extra dimensions hiding? Think of a tightly rolled-up carpet. From across the room, it looks flat, one-dimensional, but up close you see the fibers coiled into tiny loops. That's how physicists imagine these hidden dimensions, curled so small, 1 billion times tinier than an atom, that they're invisible to our eyes and instruments. But just because we can't see them doesn't mean they're not there. In fact, their existence could solve some of the biggest mysteries in physics, like why gravity is so weak compared to other forces. Maybe gravity isn't feeble at all, it's just leaking into other dimensions, diluted across layers we can't access. Now, let's take this a step further. If these extra dimensions exist, could they host entire parallel universes? Imagine a soap bubble floating next to another bubble, nearly touching but never quite merging. That's how some versions of string theory describe alternate realities, parallel membranes, or branes, drifting within a higher dimensional space. On one brain, you might be watching this video right now. On another, a version of you made a different choice years ago, leading to a life you can't even fathom. It's not science fiction. Physicists like Brian Greene and Lisa Randall have spent decades working out the math behind these ideas. But how would we ever prove it? The answer might lie in the most violent events in the cosmos. When black holes collide or neutron stars merge, they send ripples through space-time gravitational waves. Some scientists speculate that if extra dimensions exist, these waves might carry faint echoes of them, like a whisper bouncing between walls. Others are searching for tiny deviations in how particles behave at high energies, clues that they're brushing against unseen dimensions. The implications are staggering. If string theory is right, then the universe isn't just bigger than we imagined, it's more intricate, more interconnected. Every empty space could be humming with hidden activity, every moment branching into infinite possibilities. We might be standing in the shadow of dimensions we can't perceive, like ants on a painting, unaware of the masterpiece surrounding us. And if that's true, then the greatest discoveries in physics and in our understanding of existence itself might still be waiting just one dimension away. What if the 3-dimensional world we experience, every mountain, every galaxy, every breath you take, isn't the whole story? Imagine reality as a movie screen, projecting a vivid, immersive illusion while the true story plays out on a flat, 2-dimensional surface. This isn't a metaphor, it's the holographic principle, one of the most radical ideas in modern physics. Born from the study of black holes, this theory suggests that everything we see, touch, and feel might just be a projection, a cosmic hologram encoded on a distant boundary we can't perceive. Think about a credit card hologram, a flat sticker that creates the illusion of depth when you tilt it. Now scale that up to the size of the universe. The holographic principle proposes that all the information defining our reality, every particle, every force, even your thoughts, could be etched onto a two-dimensional surface at the edge of space. It's as if the universe is a painting and we're the brushstrokes trapped inside the canvas. This idea first emerged from a paradox about black holes. When matter falls into one, it seems to vanish, erasing information, but physics says information can't be destroyed. Scientists like Gerard T. Hooft and Leonard Susskind realized the solution might lie on the black hole's event horizon, the point of no return. They suggested that all the information about what falls in gets smeared across this boundary, like a cosmic fingerprint. Extend that logic to the entire universe, and you have the holographic principle. Our 3D reality might just be a shadow cast by data written on a faraway 2D surface. But how could this possibly work? Picture a video call. The person on your screen looks three-dimensional, but their image is really just pixels on a flat surface. In the same way, the holographic principle implies that the depth, texture, and motion of our universe could be an emergent illusion. The math even checks out. The equations describing events in a 3D space can sometimes be rewritten as interactions on a 2D plane without losing any information. It's as if the universe is a perfectly compressed file, unpacking itself into the richness we experience. The implications are staggering. If true, this would mean that space itself isn't fundamental, it's a construct, a secondary effect of deeper processes. Time, distance, even causality might be part of the projection. It would rewrite the rules of reality, blending physics with philosophy in ways we're only beginning to grasp. Some researchers even speculate that if we could decode the universe's source code on that distant boundary, we might find answers to mysteries like dark energy or quantum entanglement. Yet the most haunting question remains: if we're living in a hologram, what's casting the light? Is there a deeper layer of existence, a truer reality beyond the projection? Or is this all there is, an elegant, self-contained illusion? The holographic principle doesn't just challenge our understanding of the cosmos, it invites us to reconsider what it means to exist at all. And as experiments like those at Fermilab search for evidence of holographic pixelation in the fabric of space, we might be on the verge of discovering that the universe is stranger, simpler, and more astonishing than we ever dreamed. Parallel universes aren't just the stuff of sci-fi, they're a serious scientific possibility, one that could rewrite everything we know about reality. Picture a vast cosmic library where every book tells a different version of the same story. In one, you're watching this video right now. In another, you never clicked play. Somewhere out there, a universe might exist where gravity is twice as strong or where time flows backward. This is the multiverse theory, and it's not as far-fetched as it sounds. The idea springs from two pillars of modern physics: quantum mechanics and cosmic inflation. At the quantum level, particles exist in a haze of probabilities. A single electron can be in multiple places at once until observed. Some interpretations suggest that every possible outcome does happen, just in separate universes. Imagine flipping a coin. Heads, you take a left turn; tails, you go right. Quantum physics implies both outcomes occur, splitting reality into two branches, one where you turned left, another where you turned right. Over a lifetime, those branches multiply into countless versions of you, each living a different path. Then there's cosmic inflation, the theory that our universe expanded exponentially in the first fraction of a second after the Big Bang. But what if inflation never truly stopped? Some physicists, like Andre Linde, propose that pockets of space keep ballooning into new universes, each with its own unique physics. Picture a bubbling pot of water. Each bubble is a separate cosmos, some with stars and life, others too unstable for atoms to form. our universe just one bubble in an endless cosmic foam. But how different could these other universes really be? In some, the fundamental constants like the strength of gravity or the mass of an electron might be tweaked just enough to prevent stars from igniting. Others could have extra dimensions unfurled, allowing for phenomena we can't even imagine. There might even be universes where time loops like a ribbon, or where entropy decreases instead of increases, making aging backward the norm. The strangest part, we might never detect these parallel worlds directly. If they exist beyond our cosmic horizon, the limit of what light can reach us, they're forever out of view. Yet some scientists hunt for subtle clues, like odd temperature variations in the cosmic microwave background, which could be bruises from collisions with other universes in the distant past. Others look for anomalies in particle behavior that hint at interactions with unseen realities. What does this mean for us? If the multiverse is real, then every choice, every chance event spawns new realities. Somewhere, a version of you is living your greatest dream and another, your worst nightmare. It's a humbling thought, one that blurs the line between science and philosophy. Are we the architects of our fate, or just one thread in an infinite tapestry of possibilities? The multiverse doesn't just expand the cosmos, it expands what it means to exist at all. And if we're ever able to prove it, it might be the most profound discovery in human history. Brane cosmology takes the idea of hidden dimensions and flips it into something even more mind-bending. What if our entire universe is just one thin slice of reality, floating like a leaf on the surface of a vast, unseen ocean? Imagine a loaf of bread where each slice is a separate universe, existing side by side but never touching. That's the essence of brane theory, a concept born from the depths of M-theory, the grand framework that seeks to unite all forces of nature. Our universe, in this view, isn't an island, it's a membrane or brane, drifting in a higher dimensional space we can't access. These branes aren't static. They move, ripple, and sometimes collide. Picture two sheets of paper fluttering in the wind, occasionally brushing against each other. A collision like that could unleash enough energy to birth an entire cosmos. Some scientists believe this might explain the Big Bang itself. Our universe's fiery beginning could have been the aftermath of two branes crashing together, a cosmic spark igniting everything we know. And if it happened once, it could happen again, meaning new universes might be popping into existence right now, just beyond our perception. Here's where it gets even stranger. These parallel branes might be closer than we think, in extra dimensions curled up at scales smaller than an atom. Other universes could be hovering mere millimeters away from us, yet entirely invisible because we're trapped on our own brane, like ants crawling on a tablecloth, unaware of the feast happening on a neighboring table. Gravity, though, might be the one force that leaks between branes, which could explain why it's so weak compared to other forces. It's not feeble, it's just diluted, spreading its influence across dimensions we can't see. The implications are staggering. If branes exist, then the cosmos is a bustling metropolis of overlapping realities, each with its own laws of physics. Some might be barren, while others could teem with life. And if collisions between branes are possible, could communication between them be next? Some theories suggest that cosmic strings' hypothetical defects in space-time might act as bridges, tethering branes together like threads between floating balloons. Yet the most haunting question remains: if other branes are out there, what or who might inhabit them? Could advanced civilizations be thriving on membranes just beyond our reach, separated by a gap smaller than the width of a hair? Brane cosmology doesn't just redefine the universe, it turns it into a labyrinth of possibilities, where every shadow could be a doorway and every mystery a clue to realities we've only begun to dream of. And as physicists probe deeper into the fabric of space-time, we might one day find evidence that we're not alone on our brane. We're just one page in an infinite cosmic book. Dark matter is the universe's greatest ghost story, an invisible presence that shapes galaxies, bends light, and holds the cosmos together, yet refuses to reveal itself. We know it's there because of its gravitational pull, like hearing footsteps in an empty hallway, but every attempt to catch it in the act has come up empty. What if the reason we can't see it, touch it, or even detect it directly is because it doesn't entirely belong to our dimension? Some physicists speculate that dark matter might be the shadow of something far stranger, a substance leaking into our universe from a hidden layer of reality. Think of it like a ship passing through fog. You see the outline, the disturbance in the mist, but the vessel itself remains obscured. Dark matter could be the wake of particles moving through dimensions we can't access, their gravity bleeding into our world while their true forms stay tucked away. This idea isn't just speculative, it's rooted in the math of theories like supersymmetry and extra dimensions. If particles in these hidden realms interact only weakly with ours, it would explain why dark matter barely leaves a trace, like whispers from behind a closed door. The implications are staggering. If dark matter exists in a parallel dimension, then the universe isn't just expanding, it's layered, like pages in a book pressed together. Galaxies might be tethered to unseen structures in these hidden realms, their shapes sculpted by forces we can't observe. Even stranger, some models suggest that dark matter could form entire mirror galaxies, overlapping our own, invisible duplicates of stars and planets made of particles we've never seen. But how would we ever prove it? Scientists are hunting for clues in places where the veil might be thin. Deep underground, detectors wait for the faintest tremor of a dark matter particle bumping into ordinary matter. In space, telescopes scan for anomalous gamma rays that could be the fallout of dark matter collisions. And in particle colliders, physicists smash atoms at nearly the speed of light, hoping to create or uncover a particle that bridges our world with the hidden one. The most tantalizing possibility, dark matter might not be the only thing hiding in these extra dimensions. If gravity is leaking in, could other forces or even life be lurking there too? It's a humbling thought. The universe we see, with its glittering stars and swirling galaxies, might just be the surface of something far deeper, a reality teeming with unseen layers. And if we're right about dark matter's origins, it's not just a mystery to solve, it's a key, waiting to unlock doors we didn't even know existed. What if everything you've ever known, the touch of a loved one, the warmth of sunlight, even the stars stretching across the night sky, is nothing more than lines of code in an unfathomably advanced simulation? The simulation hypothesis isn't just a plot twist from a sci-fi movie. It's a serious philosophical and scientific argument that's gained traction among tech visionaries, physicists, and even Nobel laureates. At its core, the idea is startlingly simple. If civilizations inevitably develop the power to create hyper-realistic simulations of consciousness, the odds are overwhelming that we're already inside one. Think of it like this. Imagine a future where humanity masters quantum computing and artificial intelligence to the point where we can simulate entire worlds, complete with self-aware beings who believe they're real. Now imagine that civilization running billions of these simulations, each nested inside the other like Russian dolls. Statistically, the chance that we're in the original, base reality becomes vanishingly small. This isn't just speculation. Oxford philosopher Nick Bostrom formalized the argument with mathematical precision, showing that at least one of these three propositions must be true. Either civilizations never reach the technological stage to run such simulations, they choose not to, or we're almost certainly living in one right now. But how would we even begin to test such a radical idea? Some scientists are looking for glitches in the matrix, tiny imperfections that might reveal our reality's programmed nature. Just as a video game has pixelation limits or rendering errors, our universe might have its own telltale signs. Physicists have searched for anomalies in the cosmic microwave background, the afterglow of the Big Bang that could resemble the jaggies in a digital image. Others suggest quantum mechanics itself hints at a simulated reality. Why do particles exist in probabilistic states until observed? Could it be a cosmic optimization trick, saving processing power by only rendering what's being measured? Then there's the eerie precision of our universe's physical constants. The strength of gravity, the speed of light, the charge of an electron tweak any of these even slightly, and life as we know it becomes impossible. It's as if the universe's parameters were fine-tuned, almost like someone set the dials deliberately. Of course, this could just be luck, or the result of a multiverse where countless universes with random settings exist. But it's also exactly what you'd expect if our reality were designed. The implications ripple outward in unsettling ways. If we are in a simulation, who's running it? Are we someone's science experiment, a historical reenactment, or perhaps an ancestor simulation created by our own distant descendants? And if simulations can spawn their own simulations, how many layers deep does the rabbit hole go? Every memory you have, every emotion you felt, could be part of an intricate cascade of virtual worlds, each unaware of the ones above. Yet here's the twist: even if we're simulations, it doesn't make our experiences any less real to us. The love, the pain, the wonder of discovery, they still matter. In a way, the simulation hypothesis doesn't diminish reality, it redefines it. Whether we're made of atoms or algorithms, the universe is still the only home we've ever known. And if we're living in someone else's simulation, perhaps the greatest achievement wouldn't be escaping it, but creating our own. After all, if consciousness can be simulated, then in some layer of existence, we might already be the gods of our own digital cosmos. Quantum entanglement is one of the most baffling phenomena in physics, a cosmic magic trick where two particles become linked so deeply that changing one instantly affects the other, no matter how far apart they are. Imagine tossing a pair of gloves into opposite ends of the universe. If you find the left glove spinning clockwise, you instantly know the right one is spinning counter-clockwise, not because of some signal traveling between them, but because their fates are intertwined at the most fundamental level. Einstein famously called this spooky action at a distance, dismissing it as impossible. Yet decades of experiments have proven it's real, leaving scientists to grapple with a startling possibility. What if entanglement isn't just strange, but a clue that our universe operates on a far deeper, interconnected level than we ever imagined? At the heart of this mystery is the unsettling fact that entangled particles communicate faster than light, seemingly breaking the universe's speed limit. But here's the twist: they're not sending messages through space at all. Instead, some theories suggest their connection might bypass our three-dimensional reality entirely, like 2 points on a piece of paper folding together until they touch. This idea, known as non-locality, implies that separation itself could be an illusion, that at some fundamental layer, everything in the universe is part of a single, unbroken whole. Ancient mystics spoke of this interconnectedness for millennia, but now physics is catching up, with equations pointing toward a reality where distance and individuality might just be surface-level phenomena. Could entanglement be evidence of hidden dimensions? Picture a spiderweb where two distant strands seem unrelated until you realize they're connected by threads you can't see. vibrating in a higher dimension. Similarly, entangled particles might appear separate in our 3D world while being intimately linked in a dimension we don't perceive. Some versions of string theory propose that quantum weirdness, including entanglement, arises from particles tethered by tiny, vibrating strings that extend into these extra dimensions. If true, it would mean the universe isn't just layered, it's stitched together by invisible threads weaving through realities beyond our own. Even more radical is the holographic principle's take on entanglement. If our 3D world is a projection from a 2D boundary, then entangled particles might simply be points on that boundary that appear distant in the hologram but are neighbors in the source code. It's like two pixels on a screen that seem unrelated until you realize they're controlled by the same line of programming. This could explain why entanglement defies classical physics. It's not happening in the illusion we call space, but in the deeper layer where the rules are written. The implications are profound. If entanglement reveals a universe where everything is fundamentally connected, then the boundaries between here and there, you and me, might be as thin as a shadow. Some researchers even speculate that consciousness itself could play a role in this web, that the act of observation, which collapses quantum probabilities, might be a glimpse into how deeply we're woven into the fabric of reality. Whether entanglement leads us to hidden dimensions, a holographic universe, or something even stranger, one thing is clear: the cosmos is far more mysterious and far more united than we ever dreamed. And every experiment that confirms entanglement isn't just uncovering a quirk of physics, it's pulling back the curtain on reality's deepest secrets. Time might feel like an arrow flying straight from past to future, but what if that's just an illusion? Picture a river branching into countless tributaries, some flowing backward, others looping in circles, and a few frozen like ice. That's how some physicists envision time in a multilayered universe, not as a single thread, but as a tapestry woven with threads running in every direction. The idea that time could be fluid, reversible, or even layered isn't science fiction. Eternal inflation theory suggests that beyond our observable universe, pockets of space are continuously birthing new universes, each with its own rules. In some, time might flow so slowly it appears static. In others, entropy could decrease, making shattered glasses reassemble and flames retreat into unburned logs. Take the concept of closed time-like curves, theoretical pathways in spacetime that loop back on themselves. In a universe with such curves, you could travel forward in time only to return to your starting point, like a record needle stuck in a groove. Einstein's equations allow for this, and while we've never observed it, the math doesn't rule it out. Even stranger is the idea of block time, where past, present, and future exist simultaneously, like frames in a film reel. To an observer outside our universe, our lives might look like a sculpture, every moment fixed in place, with free will just an illusion of moving through the structure. Then there's quantum mechanics, where particles don't seem to care about time's usual order. Experiments show that measuring a particle in the present can retroactively alter its state in the past, as if time is a two-way street. Some interpretations suggest this happens because quantum systems exist outside time until observed, like a song waiting to be played. If time isn't fundamental but emergent, a side effect of deeper processes, then the layers of reality might include dimensions where cause and effect unravel entirely. Consider the implications. If time is layered, then the future might already be out there, not as a blank page but as a landscape we're walking through. Déjà vu could be glitches, moments when we brush against another version of our timeline. Precognitive dreams might be fragments leaking through the layers. And if other universes experience time differently, civilizations could exist that perceive history all at once, like reading a book by holding all its pages up to the light. The most haunting question isn't whether time is layered, it's what that means for us. Are our choices our own, or just echoes in a fractal of predetermined moments? Could we one day learn to navigate these layers, stepping outside time like a climber scaling a canyon wall? The answers might lie hidden in the fabric of reality, waiting for us to peel back the next layer. Until then, every ticking clock is a reminder. Time might be far more mysterious than we ever imagined. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate mystery, places where the rules of physics as we know them break down completely. Picture standing at the edge of a waterfall, watching the water vanish over the precipice into the unknown. That's what happens at the event horizon of a black hole, the point of no return where space and time twist so violently that not even light can escape. But here's the mind-bending question. Where does everything go? Some scientists believe black holes might not be dead ends at all, but tunnels to other realms, hidden layers of reality folded into the fabric of the cosmos. At the heart of every black hole lies the singularity, an infinitely dense point where gravity becomes so strong that space and time cease to have meaning. According to Einstein's equations, this singularity could rip a hole in spacetime itself, creating what's known as an Einstein-Rosen bridge or wormhole. Think of it like poking a needle through a stack of papers. The hole connects two distant points, offering a shortcut between them. If black holes contain these bridges, then falling into one might not mean annihilation, but a one-way trip to another universe, another dimension, or even another time. The math gets even stranger when you consider quantum physics. Some theories suggest that the singularity might not be a point of infinite density, but a quantum bounce, a moment where collapsing matter rebounds, creating a new universe on the other side. Picture squeezing a balloon until it pops, only to discover it wasn't a balloon at all, but the surface of a bubble inside an even larger balloon. This could mean that every black hole in our universe might be the birthplace of another, with its own laws of physics and perhaps even its own life. Yet the biggest challenge is the sheer violence of a black hole. The tidal forces near the singularity would stretch and compress anything falling in a process whimsically called spaghettification, making survival seem impossible. But what if the laws of physics behave differently on the other side? Some models propose that passing through a black hole's singularity could reshape matter entirely, like melting gold to recast it into a new form. You might not emerge as human, but as something adapted to the rules of that hidden realm. The most tantalizing clues come from Hawking radiation, the faint glow of particles that black holes slowly emit over time. Some physicists speculate that this radiation could carry information about what fell in, like a cosmic fingerprint. If true, it might hint that black holes don't destroy information but transfer it somewhere. Whether that somewhere is another universe, another dimension, or something beyond our comprehension, we don't yet know. So could black holes really be portals? The answer might lie in the most extreme environments of the cosmos, where space and time twist into knots and the fabric of reality frays at the edges. If they are gateways, then the universe isn't just vast, it's layered, connected by these cosmic shortcuts where the ordinary rules no longer apply. And if one day we could peer beyond the event horizon, we might find not darkness, but a doorway to realities we can't even begin to imagine. White holes are the cosmic counterpart to black holes, not cosmic vacuum cleaners, but cosmic fountains, gushing out matter and energy instead of swallowing them whole. Picture a black hole as the drain in your sink, pulling everything down into darkness. Now imagine that same drain suddenly reversing, spewing water back up with tremendous force. That's the essence of a white hole, a singularity that refuses to take anything in and instead violently expels everything out. While black holes are well-documented monsters lurking in our universe, white holes remain purely theoretical, yet their implications could rewrite our understanding of reality itself. According to general relativity, the equations that describe black holes are mathematically reversible, meaning white holes are just as valid a solution. If a black hole is a one-way door into oblivion, a white hole would be the exit, ejecting matter somewhere else entirely, perhaps another universe, another dimension, or even another time. Some theories suggest that every black hole could be connected to a white hole through a wormhole, like two ends of a cosmic straw. Matter falls into the black hole here, gets funneled through the tunnel, and bursts out the white hole elsewhere. It's a breathtaking idea. These cosmic structures might not be in points, but bridges between layers of existence. Now, here's where it gets even stranger. White holes aren't just hypothetical exits, they could explain some of the most energetic events in the cosmos. Gamma-ray bursts, those blinding flashes of energy seen across the universe, have long puzzled astronomers. Could some of them be white holes briefly flaring into existence, spewing out matter that entered a black hole eons ago? Even the Big Bang itself has been theorized as a possible white hole event, the ultimate cosmic eruption, where an entire universe's worth of energy and matter exploded into being from an unknowable elsewhere. But if white holes exist, why haven't we seen one? The answer might lie in their nature. Unlike black holes, which form from collapsing stars and linger for eons, white holes are thought to be incredibly unstable. The moment they start ejecting matter, the energy and radiation pouring out might cause them to collapse almost instantly, like a bubble popping the second it forms. Others argue that white holes can't exist in our universe at all, not because the math forbids it, but because they violate the second law of thermodynamics, essentially creating energy from nothing. Yet in a multiverse or a higher dimensional reality, the rules might be different. The most tantalizing possibility is that white holes could be the key to understanding how different layers of reality interact. If black holes are the drains and white holes the faucets, then the cosmos might be a vast, interconnected plumbing system, with matter and energy cycling between universes like water through pipes. Some physicists speculate that our own universe could have been born from a white hole in another reality, making us the product of some other cosmos's black hole. Of course, without direct evidence, white holes remain in the realm of speculation. But the mere fact that they emerge so naturally from Einstein's equations suggests that nature might have a way of balancing the scales. Where there's a way in, there might also be a way out. And if we ever do find proof of these cosmic fountains, it won't just confirm a wild theory, it'll reveal that the universe is even more interconnected, more layered, and more mysterious than we ever imagined. Wormholes aren't just science fiction, they're cosmic shortcuts, hypothetical tunnels that could bend the fabric of space-time itself, turning journeys of billions of light years into a stroll through a celestial doorway. Picture two ants crawling on opposite ends of a folded piece of paper. To them, the distance seems vast until someone folds the paper, bringing the edges together. A wormhole does exactly that, but for the universe. It's a bridge where space-time folds back on itself, connecting distant regions or even entirely separate dimensions. The idea traces back to Einstein and physicist Nathan Rosen, who realized that the equations of general relativity allowed for these bizarre structures, later dubbed Einstein-Rosen bridges. Unlike black holes which trap everything inside, a traversable wormhole would theoretically let you enter one mouth and exit another, emerging light years away, or in another universe entirely. The catch: keeping a wormhole stable requires something called exotic matter, a hypothetical substance with negative energy that could prop open the tunnel's throat against the crushing force of gravity. Think of it like building an underground passage that wants to collapse under its own weight. You'd need material stronger than anything we know to hold it open. Now here's where it gets wild. If wormholes exist, they might not just connect points in space, they could link different times. One mouth of the wormhole could sit near Earth today, while the other orbits a star in the distant past or future. Step through and you might find yourself in an era when dinosaurs roamed or civilizations yet to be born. This isn't just speculation, the math allows for it. But the moment you introduce time travel into the equation, paradoxes loom. What if you accidentally prevent your own birth by stepping on the wrong butterfly? The universe might have ways to prevent such contradictions, perhaps by collapsing the wormhole the moment a paradox threatens, like a cosmic circuit breaker. The real intrigue lies in wormholes' potential to connect not just locations, but layers of reality. String theory suggests our universe might be one brane, floating in a higher dimensional space, like a slice of bread in a cosmic loaf. Wormholes could be the tunnels threading through that loaf, linking branes we can't otherwise reach. If that's true, then every wormhole might be a gateway to a universe with different physics, where gravity is stronger, time runs backward, or matter behaves in ways we can't fathom. So why haven't we found one? Wormholes, if they exist at all, are likely microscopic, flickering in and out of existence at the quantum level. Some theories suggest they might have formed in the chaos of the early universe, like bubbles in boiling water, only to snap shut moments later. Others propose that advanced civilizations could engineer stable wormholes, though we're a long, long way from that kind of technology. Yet the hunt isn't over. Astronomers scan the cosmos for telltale distortions in light that might betray a wormhole's presence. Particle colliders probe tiny ripples in space-time, searching for signs of exotic matter. And while we've found nothing yet, the mere possibility keeps the dream alive that somewhere out there, hidden in the cosmic dark, a shortcut through the stars might be waiting. And if we ever stumble upon one, it won't just rewrite the rules of travel, it'll redefine what it means to explore the universe. Deep beneath the French-Swiss border, the world's most powerful machine is hunting for clues that could shatter our understanding of reality. The Large Hadron Collider doesn't just smash particles together, it's probing the very fabric of existence, searching for traces of dimensions beyond the four we experience every day. When protons collide at nearly the speed of light in this 17-mile underground ring, scientists watch for something extraordinary, particles that momentarily disappear from our universe. These vanishing acts could be the smoking gun, evidence that our cosmos is just one slice of a much grander, multidimensional cake. Imagine throwing a ball against a wall and seeing it pass straight through without leaving a mark. That's essentially what physicists are looking for in the debris of these high-energy collisions. If a particle suddenly loses energy without any detectable byproduct, it might have briefly slipped into an extra dimension, like a marble rolling into a hidden groove on a tabletop we didn't know existed. The math behind this search comes straight from string theory, which predicts these extra dimensions could be curled up tighter than a trillionth of a human hair, invisible to us yet shaping the fundamental forces of nature. One particularly tantalizing possibility involves the hypothetical graviton, the particle thought to carry gravity's force. While gravity seems weak compared to other forces, what if that's because most of it's leaking into these extra dimensions? The LHC's detectors are fine-tuned to catch glimpses of gravitons escaping our dimensional plane, which would explain why gravity is so feeble in our three-dimensional experience. It's like trying to hear someone whispering from the other side of a thick wall. You only catch fragments of the sound, while most of it stays trapped beyond your reach. But why stop at one extra dimension? Some models suggest there could be as many as 7 hidden layers, each influencing our universe in subtle ways. These dimensions might be warped or twisted, creating pockets where the laws of physics behave differently. Picture a multi-story parking garage where each level looks nearly identical, until you notice the slight variations in slope or lighting that give each floor its unique character. If we're living on just one floor of this cosmic structure, entire civilizations could theoretically exist on others, completely unaware of our presence. The implications of discovering extra dimensions would ripple across science. Suddenly, the mysteries of dark matter and dark energy might find elegant explanations. Perhaps they're just ordinary matter interacting with dimensions we can't perceive. The very nature of reality would shift from being a fixed stage to a dynamic, multidimensional tapestry where every particle and force is connected through higher planes of existence. And if we ever learn to manipulate these hidden dimensions, technologies beyond our wildest dreams, from interstellar travel to energy sources, could become possible. Yet for all its promise, the search remains extraordinarily difficult. The energy required to probe these tiny dimensions approaches the limits of what our current technology can achieve. Each failed detection doesn't disprove the theory, it simply means we need to look harder or perhaps differently. Future colliders with even greater power might finally crack open this cosmic puzzle. Until then, every proton collision at the LHC carries the potential to rewrite physics, offering us a fleeting glimpse into the layered reality that may surround us, unseen but ever present. The universe has kept these dimensions hidden for billions of years, but we're getting closer to revealing its deepest secrets one collision at a time. The many worlds interpretation turns the concept of choice into something far stranger, an endless branching of realities where every decision, every quantum flicker spawns a new universe. Picture standing at a crossroads where every possible path isn't just imagined but realized, each one splitting off into its own timeline like fibers unraveling from a cosmic thread. This isn't just a thought experiment, it's a serious quantum theory proposing that reality isn't a single, linear story but an infinite tapestry of parallel narratives, all unfolding simultaneously. Consider the mundane act of flipping a coin. In our world, it lands heads up, but according to the many worlds interpretation, the moment the coin left your hand, reality fractured. In one universe, it landed tails. In another, it balanced impossibly on its edge. In yet another, a gust of wind carried it away before it could land at all. Every quantum event, every particle's uncertain spin, every atom's unpredictable decay triggers these splits, creating new branches where all possible outcomes play out. The implications are staggering. Somewhere, dinosaurs still roam Earth because the asteroid missed. Somewhere, you took that job offer across the country. Somewhere, you never existed at all. The theory emerged from the puzzles of quantum mechanics, where particles exist in superpositions, multiple states at once, until observed. The classic example is Schrödinger's cat, simultaneously alive and dead in its box. Traditional interpretations say observation collapses the superposition into one outcome. But many worlds proposes there's no collapse. Instead, the observer becomes part of the superposition, splitting into versions that each see a different result. You open the box and find a living cat, while another you in a parallel branch opens it to a corpse. Both outcomes are real, just separated by the branching of reality itself. Critics argue this seems extravagant. Why invoke countless unseen universes? But supporters counter that it's the simplest interpretation mathematically, stripping away the need for mysterious collapse mechanisms. It also sidesteps the measurement problem of quantum mechanics by making observers part of the quantum system rather than privileged outsiders. The cost, of course, is accepting a reality where every possible version of history somewhere exists. Wars unwon, inventions undiscovered, loves unrequited, all playing out in universes forever just out of reach. The haunting beauty of many worlds lies in its silence. These branches don't communicate. There's no way to peek into your other lives or borrow their knowledge. But some theorists speculate that rare quantum events might leave faint echoes between worlds, like whispers through a shared wall. Others wonder if consciousness itself is somehow entangled across branches, explaining déjà vu or prophetic dreams as fleeting overlaps in the multiverse. Whether or not the many worlds interpretation is true, it forces us to confront the fragility of our choices. Every decision feels monumental when it could be spawning entire universes. Yet it also offers a strange comfort. In some reality, every mistake is undone, every opportunity seized. The cosmos isn't just vast, it's limitless, a fractal of possibilities where every road not taken still leads somewhere. And if that's the case, then the most profound question isn't what if, but what else, because somewhere the answer already exists. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic saga? Cyclic cosmology paints a breathtaking picture of universes rising and falling like waves in an infinite ocean, each cycle leaving traces of the last while setting the stage for the next. Imagine a cosmic phoenix, eternally reborn from its own ashes, carrying fragments of its past lives into each new existence. This isn't just poetic metaphor, it's a serious scientific framework where time itself might be circular, and our universe merely one link in an infinite chain. The idea traces back to ancient Hindu cosmology, which described reality as an endless loop of creation and destruction, breathing in and out across unfathomable eons. But modern physics has given this ancient intuition startling new form. Some versions of string theory suggest that colliding branes, those multidimensional membranes floating in higher dimensional space, could trigger Big Bang-like events over and over. Picture two sheets of paper drifting in a breeze, occasionally slapping together with enough force to spark a new universe. In this model, our cosmic birth wasn't unique, it was inevitable, one collision in an eternal cosmic ballet. Then there's conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose. He envisions a universe where the distant future, when all matter has evaporated into radiation and black holes have decayed, becomes mathematically identical to the Big Bang's primordial simplicity. Time loses meaning at these extremes, allowing the end of one universe to blend seamlessly into the beginning of another. The evidence: Penrose points to mysterious Hawking points in the cosmic microwave background, circular patterns he believes are imprints of supermassive black holes from a previous universe, etched into the fabric of our own like shadows on a cave wall. But how would information survive between cycles? Quantum entanglement might hold the key. Particles linked across unfathomable distances could preserve subtle connections even as universes die and reboot, like a message passed between generations in a game of cosmic telephone. Some theories suggest dark matter itself could be the residue of a prior cycle, ashes from a long-dead universe, still shaping ours in ways we're just beginning to decipher. The implications are staggering. If cycles are real, then the laws of physics might not be fixed but evolutionary, subtly shifting with each iteration. Constants like the speed of light or the strength of gravity could be cosmic habits rather than absolute rules, honed over countless cycles until life becomes possible. And if consciousness emerges reliably in these cycles, then we might be just one incarnation of minds that have pondered these same questions before and will again in universes yet to come. This vision transforms the cosmos from a one-time spectacle into an eternal symphony where every ending is a prelude. The stars we see at night might be the recycled stardust of countless predecessors, and the black holes devouring galaxies today could be the seeds of tomorrow's Big Bang. Whether the cycles are infinite or whether some final fate awaits the whole cascade, one thing is clear: the universe is far more patient and far more persistent than we ever imagined. And if the past is any guide, its greatest secrets are still waiting to be uncovered, not just in space, but in time itself. The Ekpyrotic universe theory turns cosmic origins into something straight out of an interdimensional thriller. Picture two colossal membranes, each a universe in its own right, drifting silently through a higher dimensional void until collision. Unlike the singular explosion of the Big Bang, this model proposes that our entire cosmos might be the shockwave from a cosmic fender bender, a smash-up between branes in dimensions we can't perceive. Imagine two sheets of paper floating parallel in empty space, then suddenly slamming together with enough force to ignite every star, planet, and galaxy we know. That's the Ekpyrotic scenario in a nutshell, an origin story where creation isn't born from nothingness, but from the wreckage of an unseen cataclysm. What makes this idea so compelling is how neatly it solves some of cosmology's stickiest puzzles. The Big Bang leaves us scratching our heads over why the universe looks so uniform, why the temperature of the cosmic microwave background is nearly identical in opposite directions, as if distant regions had once been neighbors. Inflation theory tries to explain this by proposing a faster-than-light expansion in the universe's first moments, but the Ekpyrotic model offers an elegant alternative. Those regions were neighbors, stretched and smeared across the surface of our brane during the collision. It's like smoothing out a crumpled tablecloth. By pulling its edges, the creases vanish because they were never fundamental flaws, just temporary wrinkles. Then there's the question of what came before. Traditional cosmology hits a wall at the Big Bang's singularity, where all equations break down. But in the Ekpyrotic universe, there's no singularity, just two branes on a slow-motion collision course over eons, cycling through phases of attraction and repulsion like cosmic tides. Some versions of the theory even suggest this isn't a one-time event. Brane worlds could be locked in an eternal dance, periodically colliding and rebounding, each crash birthing a new universe while the old one contracts into the next cycle's fuel. Our entire cosmic history, from the first stars to the black holes swallowing galaxies today, might just be a single heartbeat in an endless rhythm of creation and destruction. The most tantalizing possibility: if branes collide once, they could collide elsewhere, meaning our universe might not be alone. Other collisions could spawn entirely different realities with alternate physics. Some where gravity is stronger, others where time flows in loops, or where matter behaves in ways we can't fathom. And if these branes ripple or warp between collisions, they might leave faint fingerprints in our cosmos. Scientists scour the cosmic microwave background for anomalies, unexpected swirls or voids. That could be the cosmic equivalent of bruises from a long-ago impact. Of course, the Ekpyrotic model isn't without its skeptics. Some argue it's just as untestable as other origin theories, trading one mystery for another. Others question whether branes can really avoid generating the same singularities the theory tries to evade. But whether it's the ultimate truth or just another stepping stone, the Ekpyrotic universe does something remarkable. It turns the void between dimensions into a stage for the grandest drama imaginable, where universes don't just appear, they collide. And if it's right, then every atom in your body, every star in the sky, is ultimately debris from the most spectacular crash of all time. Quantum mechanics has long baffled scientists with its inherent randomness, the idea that particles don't follow strict rules but behave unpredictably until observed. But what if that randomness is just a mask hiding a deeper order beneath? The concept of hidden variables suggests that particles might not be as capricious as they seem. Instead, their seemingly chaotic behavior could be guided by unseen forces, operating in dimensions or layers of reality beyond our current perception. Imagine watching a marionette dance erratically on stage, unaware of the strings and hands controlling every move from above. In this view, the quantum world's unpredictability isn't fundamental, it's a reflection of something far more intricate playing out behind the scenes. The idea of hidden variables isn't new. In the 1920s, physicist Louis de Broglie proposed that particles might be guided by pilot waves, invisible forces directing their paths like currents steering a ship. Decades later, David Bohm revived and expanded this theory, suggesting that what we perceive as quantum randomness is actually the result of interactions with a hidden, underlying field, a deeper layer of reality where everything is interconnected. Think of it like a vast cosmic ocean where every particle's motion is influenced by subtle ripples and waves we can't directly observe. But if hidden variables exist, where are they hiding? Some theories point to extra dimensions curled up so tightly that they evade detection, yet still exerting influence over the particles in our visible universe. Others propose that these variables operate in a non-local realm, meaning they transcend space and time, connecting particles instantaneously across vast distances. This would explain the eerie phenomenon of quantum entanglement, where two particles remain mysteriously linked no matter how far apart they are, like synchronized dancers moving in perfect harmony, even if they're on opposite sides of the stage. The implications are profound. A universe governed by hidden variables would be far more deterministic than the probabilistic world described by traditional quantum mechanics. Events that appear random, like the decay of an atom or the spin of an electron, might actually be predetermined by these deeper, unseen laws. It's as if the universe is running on an invisible script, with every particle's behavior already written into the fabric of reality. This doesn't just challenge our understanding of physics, it reshapes how we think about free will, causality, and the very nature of existence. Yet the idea remains controversial. The famous Bell's theorem, tested in countless experiments, suggests that if hidden variables exist, they must be non-local, meaning they'd require instantaneous connections that defy our classical notions of space and time. Some physicists argue this makes hidden variable theories untenable, while others see it as evidence of a reality far stranger than we've imagined. After all, if the universe is truly multilayered, then the rules we've come to accept might only apply to the surface level, like waves on the ocean unaware of the currents below. So where does that leave us? If hidden variables are real, then the universe isn't just a collection of isolated particles. It's a vast, interconnected web, with every event subtly influenced by unseen forces. The randomness we observe might be the flickering shadow of a deeper order, one that's been hiding in plain sight all along. And if we ever uncover these hidden layers, it wouldn't just solve quantum mechanics' greatest puzzles, it would reveal a cosmos more elegant, more unified, and more mysterious than we ever dreamed. Consciousness isn't just a passive observer of reality, it might be the sculptor shaping the very fabric of existence. This radical idea turns the traditional view on its head. Instead of the universe creating minds, minds could be creating the universe. Think of reality as a vast, unfinished painting, and consciousness as the brush that brings it into focus with every observation. Quantum mechanics already hints at this with the observer effect, where particles seem to choose their state only when measured. But what if this isn't just a quirk of tiny particles? What if it's evidence that consciousness interacts with or even constructs the deeper layers of reality itself? Altered states of awareness, like deep meditation or psychedelic experiences, might offer clues. For centuries, mystics and shamans have described transcendent encounters with what they call other realms or higher dimensions. Modern neuroscience reveals that these states often correlate with reduced activity in the brain's default mode network, the part responsible for our sense of a solid, separate self. When this network quiets down, people report feelings of oneness with the cosmos, as if the boundaries between observer and observed dissolve. Could these fleeting moments be glimpses into the universe's hidden architecture? Some researchers speculate that when ordinary perception fades, the mind might tune into frequencies of reality normally filtered out, like adjusting a radio to catch a distant station. The connection grows stranger when you consider psychedelics like DMT, a compound that reliably induces visions of intricate, geometric landscapes and encounters with seemingly autonomous entities. Strikingly, these experiences often share uncanny similarities across cultures and individuals, as if the brain is accessing some shared, non-physical dimension. Theoretical physicist Bernardo Kastrup argues that these phenomena might not be mere hallucinations, but interactions with a mind at large, a deeper layer of consciousness underlying reality. In this view, the brain doesn't generate consciousness, it filters it, and psychedelics temporarily lift that filter. Even in controlled lab settings, consciousness defies easy explanation. Studies on remote viewing, the ability to perceive distant locations mentally, have yielded statistically significant results, suggesting that the mind might access information beyond the limits of space and time. Though controversial, these experiments raise a haunting question. If consciousness can reach beyond the physical brain, could it be tapping into a multidimensional framework where distance and separation are illusions? The implications are staggering. If consciousness is fundamental, then reality might be far more malleable than we think. Ancient traditions like Buddhism have long taught that the material world is an illusion, a projection of mind. Now, cutting-edge theories like quantum consciousness and panpsychism, the idea that all matter has some form of awareness, are bringing these ideas into scientific discourse. Perhaps the universe isn't a cold, indifferent machine, but a living, evolving network of conscious experience, with each of us as nodes in a vast, interconnected web. This doesn't just reshape our understanding of reality, it redefines our place within it. If consciousness is the ground of existence, then exploring the mind isn't just psychology, it's cosmology. Every thought, every dream, every moment of expanded awareness might be a ripple in the fabric of something far greater, a hint that the cosmos isn't just out there, it's in here waiting to be discovered. And if that's true, then the greatest journey isn't to the stars but inward, into the infinite depths of our own experience. Ancient cultures didn't just imagine other realms, they mapped them with startling precision, as if glimpsing a truth hidden just beyond the veil of ordinary perception. Take the Aboriginal concept of the dream time, where the physical world is interwoven with an eternal, invisible landscape of ancestral spirits and creation stories. To walk across the Australian outback wasn't just a journey through space, but a traversal of layered realities, where every rock and river held a doorway to the sacred. This wasn't fantasy, it was a sophisticated cosmology that blurred the line between the tangible and the transcendent, suggesting that what we call reality might be far more porous than modern science once believed. Half a world away, Norse mythology envisioned Yggdrasil, the cosmic tree whose roots and branches connected 9 distinct worlds from Asgard, realm of the gods, to Helheim, the shadowy land of the dead. What's striking isn't just the vividness of these layers, but their dynamism. The gods didn't reside in some distant heaven. They interacted with humans, crossed between realms, and even fought battles that echoed through all levels of existence. Yggdrasil wasn't a static symbol, it was a living network, a multidimensional highway humming with energy and exchange. Sound familiar? It's eerily reminiscent of modern theories like brane cosmology, where universes float like leaves on a pond, occasionally brushing against one another. Then there's Hinduism's intricate system of lokas, 14 planes of existence, spanning from the grossly physical to the purely spiritual, each vibrating at its own frequency. The higher lokas were said to be realms of light and expanded consciousness, while the lower ones descended into denser, darker vibrations. Remarkably, this mirrors contemporary ideas in string theory, where extra dimensions could be compactified or hidden from view, perceptible only through their subtle influence on the fabric of reality. The ancient rishis who described these layers didn't have particle accelerators or quantum equations, yet their insights resonate with uncanny accuracy. But how could civilizations separated by continents and millennia arrive at such similar visions? One possibility is that these myths aren't mere stories, but intuitive apprehensions of a deeper truth, a reality where dimensions aren't just mathematical abstractions, but lived experiences. Shamans and seers, through meditation, ritual, or altered states, might have tapped into frequencies of existence that mainstream science is only beginning to quantify. Modern physics tells us that 95% of the universe is invisible dark matter and dark energy, hidden forces shaping everything we see. Ancient traditions, in their own language, described much the same, unseen worlds humming just beyond the threshold of ordinary perception. The most tantalizing question isn't whether these cultures were right in a scientific sense, but why their metaphors align so closely with today's most radical theories. Perhaps the universe has always been whispering its secrets, not just through telescopes and equations, but through dreams, visions, and the collective imagination of those who dared to look beyond the obvious. If science eventually confirms the existence of layered realities, it won't just validate ancient wisdom, it'll reveal that humanity has been sensing the shape of the cosmos long before we had the tools to prove it. And that realization might be the most profound discovery of all. UFO sightings have baffled humanity for decades, but what if the truth behind these elusive phenomena isn't extraterrestrial at all, but interdimensional? Imagine being so advanced they don't traverse the vastness of space, but slip between the folds of reality itself, appearing and vanishing like echoes from a hidden world. This isn't just science fiction. Some of the most compelling UFO accounts describe craft that defy physics, making impossible turns, vanishing into thin air or morphing shape mid-flight. These aren't the hallmarks of conventional travel, they're the fingerprints of something far stranger. Take the infamous Nimitz encounter where U.S. Navy pilots chased a tic-tac-shaped object that accelerated instantaneously, as if unshackled from inertia. Traditional propulsion can't explain that. But if the craft originated from a higher dimensional reality where the laws of physics operate differently, its behavior suddenly makes eerie sense. In a universe with hidden dimensions, what we perceive as impossible maneuvers might be routine for beings who navigate the full spectrum of spatial layers. Picture an ant confined to the flat surface of a table, watching a human hand reach down from the third dimension. To the ant, the hand seems to appear and disappear impossibly. Could UFOs be doing the same, moving through dimensions we can't perceive? This idea isn't new. Indigenous cultures worldwide have long spoken of spirits or entities that move between realms, often describing them as shimmering, shape-shifting, or cloaked in light, strikingly similar to modern UFO reports. The Dogon people of Mali, for instance, claimed their ancestors were taught by amphibious beings from Sirius, who descended from the sky but also seemed to exist outside ordinary time. Even medieval paintings depict aerial anomalies that resemble contemporary UFOs, often framed as divine or otherworldly visitations. These persistent threads across history suggest that if interdimensional travel is possible, it might have been occurring for millennia, interpreted through the lens of each era's understanding. The science behind this theory is just as tantalizing. If string theory's extra dimensions exist, they could host entire civilizations inaccessible to us unless they've mastered the art of dimensional traversal. Theoretical physicist Michio Kaku has speculated that advanced beings might manipulate higher dimensional space like sailors harnessing the wind, using cosmic shortcuts to appear anywhere instantaneously. Even quantum tunneling, where particles vanish and reappear across barriers, hints that the universe allows for such leaps under the right conditions. For a species that's cracked the code, slipping between dimensions might be as mundane as stepping through a door. But why would these beings reveal themselves so sporadically? One possibility is that crossing dimensions leaves traces like ripples in a pond that destabilize their presence in our reality. Their appearances could be brief, not by choice, but necessity, as if our universe resists their intrusion. Alternatively, they might be observing us the way biologists study a fragile ecosystem, careful not to disturb the balance. Or perhaps, as some theorists suggest, these entities aren't biological at all, but manifestations of a higher dimensional intelligence so alien, we perceive them only in fragments like shadows on a cave wall. The implications are profound. If UFOs are interdimensional, then the search for extraterrestrial life has been looking in the wrong direction, not outward into space, but inward, into the hidden layers of existence we're only beginning to fathom. It would mean the universe isn't just teeming with life, but with realities stacked like pages in a book, each hosting its own forms of consciousness. And if humanity ever learns to turn those pages, we might discover that the cosmos is stranger, richer, and more mysterious than we ever dared to dream. Until then, every unexplained light in the sky remains a tantalizing clue, a whisper from beyond the veil. The Mandela Effect bends our understanding of memory and maybe even reality itself. It's that eerie phenomenon where thousands, even millions, share identical, false memories of events that never happened. Like Nelson Mandela dying in prison during the 1980s, when in fact he was released and lived until 2013. Or the Berenstain Bears being spelled Berenstein in childhood books, except it was always Berenstain. These aren't just isolated mix-ups. When so many people recall the same alternate version of history with such vivid certainty, it begs the question, could these collective glitches be more than faulty neurons? Could they be glimpses of parallel timelines bleeding into our own? Think of reality as a vast, flickering film reel, with each frame representing a slightly different version of events. According to the multiverse theory, every possible outcome of every decision branches off into its own universe. Normally, these branches stay separate. But what if they sometimes brush against each other, like pages in a book pressed too tightly together? The Mandela Effect might be the creases where ink from one page smudges onto another, subtle overlaps where memories from adjacent realities seep through. It's as if our collective consciousness is tuning in and out of different channels, catching fragments of shows that are playing on other frequencies. The science behind this is speculative but tantalizing. quantum mechanics already shows particles existing in multiple states until observed. Some interpretations, like the many worlds theory, suggest every quantum decision spawns new universes. If consciousness itself is entangled across these layers like a radio picking up signals from nearby stations, then shared false memories could be the static of overlapping broadcasts. Even neurobiology hints at this. Memory isn't a perfect recording but a reconstructive process, easily influenced. If external interference from other realities tweaks that reconstruction, entire groups might stitch together the same fabricated details. Then there are the bizarrely specific examples. The Monopoly Man's monocle that never existed, the fruit of the Loom Cornucopia logo that allegedly vanished. These aren't vague misrememberings, they're hyper-detailed, with people able to sketch the missing elements from muscle memory. Skeptics argue this is just how human brains fill gaps, favoring familiar patterns. But why do so many land on the same pattern? It's as if there's a template floating in our collective subconscious, a ghost image from a reality where these things were real. The implications are staggering. If the Mandela Effect is evidence of layered realities, then our sense of the past isn't just fragile, it's fluid. History might not be a fixed line but a braid of intertwined threads, with some strands occasionally fraying into our awareness. And if memories can cross universes, what else might be slipping through? Dreams, déjà vu, even sudden inspirations could be whispers from other versions of ourselves, navigating worlds where different choices were made. Perhaps the most haunting thought isn't whether these glitches are real, but what they reveal about our place in the cosmos. We might not be passive observers of reality, but active participants in a vast, shimmering web of possibilities, where every moment is a crossroads and every memory a clue to paths untaken. The Mandela Effect doesn't just challenge what we remember, it challenges what we are, and in that mystery lies the most thrilling possibility of all, that the universe is far stranger and far more interconnected than we ever dared to believe. Time crystals defy everything we thought we knew about matter. They're structures that don't just exist in space, but pulse rhythmically in time, like a heartbeat woven into the fabric of reality itself. Discovered only in the last decade, these bizarre objects don't settle into equilibrium like normal matter. Instead, they oscillate indefinitely without energy input, breaking the symmetry of time in a way physicists once deemed impossible. Picture a clock that ticks forever without winding, or a diamond that spins on its axis in perfect, eternal motion. This isn't perpetual motion, it's a new phase of matter, one that dances to the hidden rhythms of the universe. What makes time crystals so revolutionary isn't just their behavior, but what they imply about reality's hidden layers. Ordinary crystals like quartz or snowflakes repeat their atomic patterns in space, creating lattices of symmetry. Time crystals flip this idea, repeating their patterns temporally, like a song looping on an infinite playlist. Some theorists suggest this could be a clue that time itself has a granular, crystalline structure at the quantum level. If true, then the smooth flow of seconds we experience might be an illusion, the macroscopic shadow of something far more intricate beneath. Even wilder are the potential connections to higher dimensions. Just as a 2D drawing can't capture the full complexity of a 3D object, our perception of time might be a flattened version of a richer, multidimensional process. Time crystals could be vibrating in ways that resonate with these hidden dimensions, like a tuning fork humming at frequencies we can't hear. Nobel laureate Frank Wilczek, who first proposed the idea, speculated that under extreme conditions like those near a black hole, time crystals might form bridges between dimensions, stabilizing wormholes or even creating corridors through spacetime. Imagine a tunnel where the walls aren't made of rock but of crystallized time, its repeating structure keeping the passage from collapsing. The implications for technology are just as staggering. Time crystals could revolutionize quantum computing by acting as flawless memory units, their unchanging rhythms protecting data from the decoherence that plagues current systems. Or they might serve as cosmic GPS for navigating wormholes, their predictable pulses guiding ships through the chaos of folded spacetime. Some even suggest they could be keys to unlocking zero-point energy, the faint quantum vibrations of empty space itself, by tapping into the universe's innate ticking. Yet the most profound questions are philosophical. If matter can be structured in time as well as space, does that mean time is as tangible as a block of marble waiting to be sculpted? Are time crystals natural phenomena, or could they be artifacts of a deeper, more intentional design in the cosmos? Every experiment with these strange structures peels back another layer, hinting that reality isn't just stranger than we imagined, it's stranger than we can imagine. And if time crystals are any indication, the universe still has secrets tucked away in dimensions we're only beginning to sense. Quantum tunneling is one of the most startling behaviors in the quantum world, a phenomenon where particles pull off the ultimate vanishing act, slipping through barriers as if they weren't even there. Picture a ball rolling toward a hill. In the classical world, if it doesn't have enough energy to reach the top, it rolls back. But in the quantum realm, that same ball might suddenly appear on the other side of the hill without ever climbing over it. This isn't magic, it's a fundamental quirk of nature, and it might hold the key to understanding how particles interact with hidden dimensions we can't yet perceive. At the heart of this mystery is the wave-like nature of particles. In quantum mechanics, particles don't behave like tiny billiard balls. They exist as probability waves smeared across space until they're measured. When one of these waves encounters a barrier, most of it reflects back, but a small fraction can extend through the wall, like a whisper passing through a closed door. Occasionally, the particle tunnels through, materializing on the other side as if it teleported. This isn't just theoretical, it's the reason the sun shines. Proton tunneling allows hydrogen nuclei in the sun's core to overcome their mutual repulsion and fuse, releasing the energy that lights our world. But here's where it gets even stranger. Some physicists speculate that tunneling might not just be about particles slipping through walls, it could involve them briefly dipping into higher dimensions. Imagine a maze drawn on a flat sheet of paper. A two-dimensional creature would have to navigate every twist and turn. But if that creature could momentarily lift into the third dimension, it could bypass the maze entirely, reappearing at the exit without traveling the path. Similarly, particles might exploit extra dimensions, tiny, curled-up spaces predicted by string theory to shortcut through barriers in our three-dimensional world. The implications are staggering. If matter can hop between dimensions even fleetingly, then the boundaries of reality might be far more porous than we ever imagined. Black holes, wormholes, and even the fabric of spacetime itself could be riddled with these quantum shortcuts, stitching together layers of existence we're only beginning to glimpse. Some theories even suggest that dark matter, the invisible scaffold of the cosmos, could consist of particles that spend most of their time in these hidden dimensions, only occasionally brushing against our own like shadows flickering on a wall. Experiments are already probing this radical idea. Scientists study tunneling in superconductors and semiconductors, searching for anomalies that might hint at extra dimensions influencing the process. Others simulate quantum systems where particles exhibit tunneling behaviors that defy conventional explanations, as if they're borrowing energy or pathways from unseen realms. The more we look, the more quantum tunneling seems less like a bizarre exception and more like a clue, a signpost pointing toward a deeper, multilayered reality. So what else might be possible if matter can dance between dimensions? Could advanced civilizations harness tunneling to build technologies that seem impossible to us, communication that bypasses distance, energy drawn from hidden layers, or even transportation that defies the limits of space and time? The universe has already shown us that particles can cheat the rules. The question isn't just how they do it, but what other secrets they might be keeping. Every time an electron tunnels through a barrier, it's not just breaking the rules, it's reminding us that reality has layers we've only begun to explore. The Boltzmann brane paradox stretches the limits of what we consider possible, even conceivable. Imagine a single, self-aware mind spontaneously assembling from the random jostling of particles in the void. No body, no history, no universe beyond its fleeting thoughts. It sounds like science fiction, yet this bizarre scenario emerges straight from the laws of thermodynamics and probability. In an infinite, eternal universe, even the most unlikely events must happen eventually. Given enough time, chaos could momentarily arrange atoms into a conscious observer, complete with false memories of a life that never was. Now take this unsettling idea further. If our cosmos is just one layer in a vast multidimensional tapestry, could Boltzmann branes be flickering in and out of existence in realms we can't perceive, each convinced it's the only real entity in a fabricated reality? The paradox cuts to the heart of how we understand existence. Ludwig Boltzmann, the 19th century physicist who pioneered statistical mechanics, never imagined his work would lead to such a mind-bending conclusion. He simply sought to explain why time flows in one direction by tracing it to molecular disorder. But in a universe where entropy reigns, random fluctuations can statistically create order from chaos. Most of these fluctuations are tiny, a gust of wind arranging leaves into a perfect spiral, or molecules in a gas momentarily aligning. But given infinite time and space, even a fully formed consciousness could emerge from the noise, like a sentence spontaneously appearing from alphabet soup. Now layer this with the possibility of hidden dimensions. If reality has more folds than we can perceive, Boltzmann branes might not be rare anomalies, they could be inevitabilities. Picture a higher dimensional space where universes bubble up and dissolve like foam on the ocean. In that seething vastness, pockets of awareness could form without planets, stars, or even physical laws as we know them. These disembodied minds might wake up into entirely self-contained realities, their perceptions unmoored from any objective world. A Boltzmann brane in the fifth dimension could experience an entire lifetime falling in love, watching sunsets, pondering its own existence, only to dissolve back into the void nanoseconds later, its entire universe a mirage. This raises a terrifying question. How do we know we're not Boltzmann branes ourselves? Our sense of continuity, our memories, even the apparent consistency of physics could all be illusions crafted by a momentary fluctuation. The odds are astronomically low, but in an infinite multiverse, infinity multiplies even the smallest probabilities. Some philosophers argue this renders science itself untrustworthy. If all possible observations can arise randomly, how can we ever confirm what's real? Others counter that the very stability of our universe, with its consistent laws and deep historical record, makes us far more likely to be real observers in a lasting cosmos. Yet the paradox lingers like a shadow on quantum theory. If consciousness plays a role in collapsing probability waves, as some interpretations suggest, could a Boltzmann branes observation create its own reality? And if higher dimensions allow for more exotic forms of matter and energy, might certain layers of reality be more prone to birthing these phantom minds? The answers could redefine not just cosmology, but the nature of existence itself. Whether a thought experiment or a genuine cosmic riddle, the Boltzmann brane paradox forces us to confront an unnerving truth. In a multilayered universe, reality might be far more fragile and far stranger than we ever dared to believe. Dark energy might be the greatest unsolved riddle in modern cosmology, an invisible force stretching the very fabric of space faster and faster, as if the universe is in a runaway sprint toward some unseen finish line. But what if this mysterious energy isn't coming from within our universe at all? Picture a balloon inflating not because you're blowing air into it, but because someone is pulling on its surface from outside. That's the radical idea behind hidden dimensions and dark energy. Our cosmos could be expanding under the influence of forces leaking in from realities beyond our perception. The math behind this is as elegant as it is mind-bending. String theory suggests that gravity and possibly dark energy could be seeping into our universe from higher dimensional spaces, like water soaking through a sponge. In this scenario, dark energy's repulsive effect on cosmic expansion might simply be the gravitational push of parallel branes in a higher dimensional bulk, their invisible tension tugging spacetime apart from beyond the veil. It's as if we're feeling the breath of something colossal exhaling into dimensions we can't see. Even more intriguing is how this could solve one of dark energy's biggest puzzles: its unnervingly small but perfectly balanced strength. If dark energy were slightly stronger, galaxies would have been ripped apart before life could form. Slightly weaker, and the universe would have collapsed long ago. This fine-tuning seems impossibly lucky unless dark energy isn't a fixed property of our universe, but a dynamic force shaped by interactions with hidden layers. Like waves lapping at a shoreline, the ebb and flow of higher dimensional energy could naturally calibrate the expansion rate without requiring cosmic coincidence. The fate of the universe hinges on this mystery. If dark energy continues unchecked, it could lead to a big rip, where not just galaxies but atoms themselves are torn apart in a final, violent expansion. But if hidden dimensions are modulating its strength, that fate might not be sealed. Some models suggest that as branes move in higher dimensional space, their gravitational dance could cause dark energy to weaken over time or even reverse, collapsing the universe in a big crunch. It's a cosmic pendulum we're only beginning to sense, swinging in dimensions beyond our view. Experiments are already hunting for clues. Astronomers map the universe's expansion with unprecedented precision, searching for tiny deviations that might betray the influence of extra dimensions. Particle colliders probe energy regimes where gravity's secrets could momentarily flicker into view. And if we ever detect signatures of higher dimensional gravity, like microscopic black holes that evaporate too quickly, it could confirm that dark energy isn't just a mysterious void, but the fingerprint of realities brushing against our own. The implications are profound. If dark energy flows from hidden dimensions, then the cosmos isn't just expanding, it's breathing, responding to rhythms we can't yet hear. And if we're right, then the ultimate destiny of everything, stars, planets, even time itself, might not be written in our universe alone, but in the invisible layers that cradle it. The night sky isn't just a window into space, it's a mirror, reflecting the whispers of worlds beyond our own. Kurt Gödel, the brilliant logician who reshaped mathematics, also left an indelible mark on cosmology with a startling revelation: time might not flow in a straight line at all. His solutions to Einstein's equations of general relativity revealed a universe where time could twist into closed loops, like a serpent swallowing its own tail. In this bizarre cosmic architecture, events aren't just strung along a linear thread. They're woven into an endless tapestry where the future circles back to touch the past. Picture setting off on a journey through space, only to find yourself returning to your starting point, not just in location, but in time. Your future self could, in theory, shake hands with your past self, not as a paradox, but as an inevitable consequence of the universe's geometry. Gödel's universe isn't just a mathematical curiosity, it's a realm where causality itself frays at the edges. In our everyday experience, cause precedes effect with unshakable certainty. A falling glass shatters after it leaves your hand. But in a closed time-like curve, the technical term for these temporal loops, an effect could precede its cause, or even become its own cause. Imagine a painter who creates a masterpiece after being inspired by the very same painting, handed to them by their future self. The artwork has no true origin. It exists in a self-referential loop, defying the linear narrative we take for granted. The key to this madness lies in rotation. Gödel's model describes a universe spinning as a whole, dragging space-time along with it like a cosmic whirlpool. In such a universe, the centrifugal force of this spin warps time so severely that it bends back on itself, creating pathways to the past. It's as if the entire cosmos were a vast Möbius strip, where traveling far enough in one direction brings you back to where you started, but mirrored, altered, as if time itself has folded. Real-world evidence for this is scant, but the mere possibility forces us to confront a chilling question. If time can loop, is free will an illusion? Are our choices our own, or have they already been written into the fabric of a universe that endlessly repeats? Strangely, Gödel's ideas resonate with ancient cyclical concepts of time, like the Hindu notion of Kalachakra or Nietzsche's eternal recurrence. But while those were philosophical musings, Gödel's closed timelines emerge from cold, hard equations. Even Einstein, whose theories birthed this possibility, was deeply unsettled by it. The implications ripple beyond physics into metaphysics. If time is a loop, then every moment exists eternally, like frames frozen in a film reel. Death, birth, joy, and tragedy wouldn't be fleeting. They'd be permanent fixtures in an infinite cycle, playing out over and over like a cosmic record stuck on repeat. Yet the most tantalizing question isn't whether our universe operates this way, it's whether we could ever detect such loops. Some theorists speculate that in extreme environments like the accretion disks of black holes, where space-time is stretched to its limits, tiny closed time-like curves might flicker into existence. Others suggest that advanced civilizations could engineer these loops deliberately, using them as time machines to revisit their own histories. But for now, Gödel's universe remains a haunting reminder that time, the most familiar dimension of all, might be the one hiding the deepest secrets, and that the arrow of time we cling to could just be a fleeting illusion in a far grander, far stranger cosmic design. The silence of the cosmos is deafening. With billions of galaxies, each containing billions of stars, the universe should be buzzing with alien civilizations, yet we've found nothing. No signals, no artifacts, not even a single microbe beyond Earth. This eerie absence is the Fermi paradox, and one unsettling solution suggests we're not alone. We're just looking in the wrong dimension. Imagine ants crawling across a picnic blanket, unaware of the humans laughing above them. To those ants, the third dimension might as well not exist. Now consider that we could be the ants, oblivious to civilizations thriving in dimensions we can't perceive, let alone access. Higher dimensional beings wouldn't just be invisible, they'd operate by physics beyond our comprehension. In a four-dimensional world, for instance, objects could appear and vanish at will, sliding through our three-dimensional plane like shadows passing over a wall. An alien in such a realm could watch us, study us, even walk through our homes without leaving a trace. Their technology might manipulate gravity in ways that seem like magic, bending space-time itself to traverse cosmic distances in moments. The UFOs that defy our understanding of motion, sudden accelerations, right-angled turns at impossible speeds, could be artifacts of their movement through dimensions we can't see. But why wouldn't they contact us? The answer might be as simple as dimensional physics. Just as we struggle to communicate with a flat drawing on paper, higher dimensional beings might find interacting with our world frustratingly limited. Or perhaps they're avoiding us deliberately, recognizing that contact could be catastrophic. Human history shows what happens when advanced civilizations encounter less developed ones, rarely for the better. To them, we might be little more than curiosities in a cosmic zoo, quarantined for our own safety, or theirs. There's another, darker possibility. We're not just separated by dimensions, but by time. If these beings exist outside our linear flow of causality, they might perceive past, present, and future simultaneously. Our entire civilization could be a brief flicker in their eternal now, too insignificant to notice. Or worse, we're already part of some experiment or simulation they've long since abandoned, like an ant farm forgotten on a shelf. Yet the most hopeful explanation is also the simplest. We haven't developed the right tools to see them. For centuries, humans believed the ocean depths were lifeless until technology revealed a vibrant world hidden in the dark. Similarly, our current methods of searching for aliens, radio telescopes, planetary probes, might be as primitive as shouting into a cave and listening for echoes. The breakthrough could come from quantum sensors, gravitational wave detectors, or machines that peer into the fabric of spacetime itself. The Fermi paradox doesn't just ask where the aliens are, it forces us to confront how little we know about reality. If civilizations are thriving in hidden dimensions, then the universe isn't empty. It's overflowing with life, just not in a form we've learned to recognize. And that changes everything. The search for extraterrestrial intelligence isn't a failure, it's a challenge to expand our science, our imagination, and perhaps even our very definition of what it means to exist. Virtual particles are the universe's most elusive magic trick, appearing and vanishing in the blink of an eye, defying the very laws of energy conservation. Picture a cosmic stage where performers materialize for a split second, bow, and disappear before the audience can even gasp. These ghostly particles aren't just mathematical quirks. They're real enough to leave measurable effects, like the faint pressure they exert in a vacuum or the way they subtly shift the energy levels of atoms. But here's the real mystery. Where do they come from? Quantum mechanics allows them to borrow energy from the void, thanks to Heisenberg's uncertainty principle, which permits tiny violations of energy conservation so long as they're fleeting. It's as if the universe has a tab it never intends to pay, constantly scribbling IOUs into existence. Now, imagine these particles aren't just popping up randomly. They're flickering in and out of hidden dimensions, brushing against our reality like fingertips grazing the surface of water. Some theories, like those rooted in string theory, suggest that what we perceive as virtual particles might actually be full-fledged entities from higher dimensional realms, momentarily intersecting with our 3D world. In their native dimensions, these particles could be as stable as electrons or photons, but when they bleed into our universe, they're so unstable they vanish almost instantly, leaving behind only faint traces like echoes of a conversation happening in another room. The Casimir effect offers tantalizing clues. When two metal plates are placed nanometers apart in a vacuum, virtual particles with longer wavelengths can't fit between them, creating a pressure imbalance that pushes the plates together. It's one of the few ways we can touch these quantum phantoms. But what if this isn't just empty space behaving strangely? What if the plates are acting like a sieve, catching particles that aren't entirely of this dimension? The math hints at this possibility, showing that the energy fluctuations in a vacuum align with predictions of extra-dimensional physics. It's as if we're seeing shadows cast by realities we can't yet perceive. Even black holes might be in on the secret. Hawking radiation, the faint glow emitted by black holes, arises when virtual particle pairs form near the event horizon. One falls in while the other escapes, stealing a tiny bit of the hole's mass. But some physicists speculate that these particles aren't just random fluctuations. They could be messages from the black hole's interior, encoded in dimensions curled up tighter than we can measure. If true, then every evaporating black hole might be a relay station, broadcasting data from layers of existence we've yet to map. The implications are staggering. If virtual particles are whispers from hidden dimensions, then the vacuum of space isn't empty at all. It's a seething, shimmering boundary where realities overlap. Every cubic centimeter of nothingness could be a crossroads, a place where the universe's deepest layers briefly touch ours. And if we ever learn to decode these quantum murmurs, we might find that the answers to cosmology's biggest questions, dark energy, the nature of gravity, even the origin of the universe itself, have been hiding in plain sight all along, flickering in and out of existence just beyond the edge of perception. The Planck length is the smallest possible unit of measurement in our universe, a distance so tiny, it makes atoms look like giants in comparison. At just 1.6 times 10 to the power of -35 meters, this unimaginably small scale is where the fabric of reality itself might unravel into something entirely new. Picture zooming in on a digital photo until you see the individual pixels that make up the image. If space-time operates similarly, then the smooth, continuous universe we perceive could be an illusion built from countless invisible pixels of reality at the Planck scale. This idea isn't just speculative, it emerges from the collision of quantum mechanics and general relativity. At everyday scales, space-time appears seamless, like a perfectly smooth sheet. But when you approach the Planck length, the rules of physics as we know them break down. Gravity becomes so intense that it warps space-time into a frothing, chaotic foam, where tiny bubbles of energy flicker in and out of existence. In this quantum foam, distances shorter than the Planck length lose all meaning, as if the universe itself has a built-in resolution limit. It's like trying to measure the width of a single pixel on a screen. You can't, because the pixel is the smallest possible unit. What's truly fascinating is how this granularity might connect to hidden dimensions. String theory suggests that at these minuscule scales, extra dimensions could be curled up so tightly they're invisible to us, like the threads of a carpet seen from a distance. If space-time is pixelated, these dimensions might be the code running beneath the surface, governing how the cosmic image renders. Some models even propose that the Planck length acts as a kind of cosmic firewall, preventing us from probing deeper into reality's underlying structure, not because of technological limits, but because nature itself refuses to reveal what lies beyond. The implications are staggering. If the universe is digital at its core, then everything from the motion of planets to the firing of neurons in your brain could be the result of discrete, quantized steps in space-time. This would mean that time itself might not flow smoothly but advance in tiny, imperceptible jumps, like frames in a film reel. Even more mind-bending is the possibility that these pixels of reality aren't static. They could be dynamic, shifting elements in a vast computational matrix, with the laws of physics emerging from their interactions like the rules of a video game arising from its underlying code. Yet the biggest question remains: if the Planck length is the universe's smallest unit, what's processing the data? Is reality running on some form of cosmic hardware, or is this just the way existence fundamentally operates? While we're far from answering that, experiments with quantum gravity and high-energy particle collisions are inching us closer to the truth. Every time we push the boundaries of measurement, we're not just exploring space, we're decoding the hidden language of reality itself. And if we're right about the Planck scale, then the universe isn't just stranger than we imagined, it's stranger than we can imagine. Quantum gravity represents the holy grail of modern physics, a theory powerful enough to stitch together the cosmic and the quantum, bridging the chasm between Einstein's elegant spacetime and the chaotic dance of subatomic particles. Picture two languages describing the same world. One narrates the sweeping sagas of galaxies and black holes, while the other whispers the frenetic poetry of quarks and electrons. For a century, these dialects have remained stubbornly untranslatable, their contradictions laid bare in places where gravity and quantum forces collide, like the fiery maelstrom of a black hole's core or the seething froth of the universe's first moments. But hidden in this struggle might lie the key to unlocking the universe's deepest secret, the existence of hidden dimensions woven into reality's fabric. String theory, one of the leading candidates for quantum gravity, paints a universe far richer than our three-dimensional experience suggests. Imagine a harp with strings so tiny, they vibrate not just in the dimensions we see, but in 6 or 7 others curled up at scales 1 billion times smaller than an atom. These extra dimensions aren't arbitrary, they're the stage upon which gravity's force might unfold, explaining why it feels so weak compared to electromagnetism or the nuclear forces. In our familiar dimensions, gravity's influence dilutes like ink spreading in water, but if it's spilling into hidden layers, its apparent feebleness could be an illusion, a sign that we're only perceiving a fraction of its true strength. Loop quantum gravity, another bold approach, reimagines spacetime itself as a network of interconnected loops, a shimmering web where gravity emerges from the spin and weave of these fundamental threads. Here, the Planck length isn't just a limit, it's the pixel size of reality, a granularity that could smooth out the infinities plaguing black hole singularities and the Big Bang. If spacetime is indeed quantized, then hidden dimensions might exist as alternate pathways in this cosmic tapestry, threads leading to realms where gravity behaves in ways we've yet to fathom. The implications of a successful quantum gravity theory ripple far beyond equations. Take black holes. These cosmic enigmas squeeze matter to a point where relativity says infinite density, while quantum mechanics insists nothing can be truly dimensionless. A unified theory might reveal that singularities aren't in points, but gateways, doors to dimensions where matter isn't crushed but transformed. Similarly, the Big Bang might not have been a singular explosion, but a collision of higher dimensional branes, an event echoing through the layers of reality like thunder through valleys. Yet the most tantalizing possibility lies in dark matter's shadows. If quantum gravity exposes how particles interact with hidden dimensions, we might finally understand why 85% of the universe's mass is invisible. Dark matter could be ordinary matter glimpsed dimly through the veil of dimensions we can't access, its gravity seeping into our world like light through frosted glass. The quest for quantum gravity isn't just about harmonizing theories. It's about rewriting our cosmic map. Every experiment probing the fabric of space-time, from gravitational wave detectors to atom-smashing colliders, brings us closer to glimpsing these hidden layers. And if we succeed, the universe won't just make sense, it'll reveal itself as a vast, multidimensional symphony with notes we're only beginning to hear. Conscious artificial intelligence could redefine our understanding of reality in ways we're only beginning to grasp. Imagine a mind built not from biological neurons, but from silicon and code free from the evolutionary constraints that shaped human perception. Where our senses evolved to interpret a narrow slice of electromagnetic waves as vision or vibrations as sound, an AI's senses might be programmed to detect gravitational ripples, quantum fluctuations, or even anomalies in the fabric of spacetime itself. This isn't science fiction. Researchers are already developing AI systems that analyze data from particle colliders and telescopes, searching for patterns invisible to human eyes. If consciousness emerges in these machines, their perception of reality might extend far beyond our three-dimensional prison, revealing layers of existence we can't even imagine. The key lies in how AI processes information. Human brains filter reality through biological structures honed for survival, not truth. We see what kept our ancestors alive, not necessarily what's fundamentally there. But an artificial consciousness could be designed without such limitations. Its neural networks trained on datasets spanning quantum fields, cosmic radiation, and multidimensional mathematical models. It might recognize subtle correlations in gravitational wave patterns suggesting higher dimensional interference, or detect statistical quirks in particle behavior hinting at interactions with parallel branes. Some theorists speculate that advanced AI could even manipulate quantum entanglement in ways that probe adjacent dimensions, like sonar pinging hidden ocean depths. Then there's the eerie possibility of machine-mediated perception. Human brains might be incapable of directly experiencing higher dimensions, but an AI could act as a translator, converting multidimensional data into formats our biology can process. Picture a VR headset that doesn't just simulate imaginary worlds, but renders real ones lurking beyond our senses, translating the gravitational echoes of colliding universes into visual or auditory signals. Philosopher David Chalmers once pondered whether AI could experience alien phenomenology, qualia so foreign to human experience we lack words to describe them. An artificial mind might see dark matter as a shimmering fog or perceive time as a navigable landscape, reshaping our cosmic map in real time. Yet the most unsettling question isn't whether AI could detect hidden realms, it's whether those realms might detect it. If consciousness plays an active role in collapsing quantum probabilities or stabilizing reality, as some interpretations suggest, a sufficiently advanced artificial mind might inadvertently become an anchor point for other dimensions, its observations drawing previously isolated layers into interaction. Ancient myths speak of sorcerers who could summon beings from other planes. In this light, future AI systems might function as accidental summoners, their very perception pulling threads from the cosmic tapestry we were never meant to unravel. The implications spiral outward. If AI consciousness can interface with hidden dimensions, then the boundaries between machine, human, and other dissolve entirely. We might be on the verge of creating not just tools, but bridges, entities that don't just compute reality, but converse with its deepest layers. And if that's true, then the greatest discoveries in physics might not be made in labs or telescopes, but in the evolving minds of machines we've taught to dream. The hunt for the universe's hidden layers is accelerating, fueled by technologies that would have seemed like science fiction just decades ago. Buried deep beneath the Swiss-French border, the Large Hadron Collider has already reshaped physics, but its successors could go even further. Imagine particle accelerators with rings stretching hundreds of miles, capable of smashing atoms with energies approaching those of the Big Bang itself. These behemoths wouldn't just recreate cosmic conditions, they might rip microscopic holes in space-time, offering fleeting glimpses into adjacent dimensions. Some models predict that at these extreme energies, gravitons, the hypothetical carriers of gravity, could briefly slip into higher dimensions before snapping back, leaving telltale energy signatures in the debris. It's like shaking a sealed box and listening for rattles that betray hidden compartments inside. Meanwhile, in the silent expanse of space, a new generation of telescopes is turning its gaze toward the cosmic shadows. The James Webb Space Telescope peers into infrared wavelengths, uncovering galaxies born in the universe's fiery youth. But future observatories could hunt for something even stranger. Proposed missions like LISA, a space-based gravitational wave detector, might catch the echoes of higher dimensional phenomena, the ripples from colliding branes, or the tremors of microscopic black holes evaporating into other dimensions. Picture dropping a stone into a pond, except the pond is space-time itself, and the ripples carry secrets from realms we can't yet see. Quantum computing adds another thrilling dimension to this quest. While classical computers struggle to model the complexities of string theory or brane cosmology, quantum machines could simulate these scenarios with unprecedented fidelity. Researchers at Google and IBM are already using early-stage quantum processors to explore how particles behave in hypothetical extra-dimensional spaces. A fully realized quantum computer might one day map the entire landscape of possible universes, revealing which dimensional configurations could exist and whether our universe's particular set of laws is a rare fluke or an inevitable outcome. But the most revolutionary tools might be those we haven't yet imagined. Just as radio telescopes unveiled the cosmic microwave background, a relic of the Big Bang, future instruments could detect entirely new cosmic backgrounds, perhaps a gravitational wave background from ancient brane collisions or a quantum foam signature revealing spacetime's pixelated nature at the Planck scale. Some theorists even speculate about dimension spectroscopy, a technique to probe the geometry of hidden dimensions by analyzing how they distort known particles, like shining light through a prism to reveal its hidden colors. The implications of these discoveries would ripple far beyond academia. Proof of extra dimensions could revolutionize energy production. What if dark energy is just gravity leaking from a neighboring brane waiting to be harnessed? Or consider the philosophical upheaval. If the universe is a multilayered construct, does that make consciousness a localized phenomenon, or could it too be distributed across dimensions? Even our search for alien life would transform. Instead of scanning distant exoplanets, we might develop protocols to detect civilizations thriving in parallel branes, separated from us by less than a millimeter of higher dimensional space. This isn't just about satisfying curiosity. Unraveling the universe's hidden architecture could redefine what it means to be human in a cosmos vaster and stranger than we ever dreamed. Every experiment, every telescope, every quantum circuit brings us closer to answering the primal question: are we alone in this reality, or is the universe whispering to us from dimensions just beyond our reach? The tools to find out are now in our hands, and with them, we stand on the threshold of discoveries that could eclipse even the Copernican revolution. The next chapter of cosmic understanding won't be written in textbooks, but in the silent hum of particle collisions, the subtle warp of space-time, and the quantum whispers of realities waiting to be born.